Thanks so much. My name is Ines Benguirat. I will be presenting our work, blending different traffic latency with better mixing, and this is a joint work with my co-authors, Dabajuti Das and Claudia Diaz. So before I start describing our work, I'll start with giving an overview to the field, which falls under the umbrella of MixNet. What is MixNet? MixNet is a type of anonymous communication network that prevents an adversary, very powerful adversary, global adversary, who's observing all the network links to know who is communicating with whom. This is achieved by having these servers, which we call mixes, that they will delay messages for a certain amount of time t before forwarding them to the next entity in the path, so that this adversary who is observing these mixes cannot correlate the input and output. For our work, we will focus on a layer topology, meaning that these mixes are organized in layers and they receive messages from the previous entities in the previous layer, and they will forward them to the next entities, either mixes or the final destination in the next layer. And the messages are encrypted in reverse orders. That means that first we encrypt it with the public keys of the last mix or the last entity in the path, and then the second, and then the first. And we will focus on Poisson mixing, which means that these messages will be delayed for a certain amount of time t inside of each one of these mixes, and each of these delays is withdrawn from an exponential distribution with a parameter lambda. So this is kind of the overview of our work. Typically in MixNet, it's being used usually or being described for one application. So we usually say in MixNet papers, this can be used for sending emails or can be used for sending instant messages. What that means is these delays, they are withdrawn from the same exponential distribution with the same lambda. But in this work, we wanted to explore what happens if we blend different applications on different MixNet. What that means is, let's say I want the users to use the same MixNet for sending instant messages and for sending emails. So we do know that users will have different latency tolerance when it comes to instant messages. So for example, if I send a message using Telegram, I will expect my message to be received by 5 seconds maximum. This is just an example. I might be a bit tolerant when it comes to email, where I can tolerate to up to 1 minute if I am sending an email, and maybe I'm even more tolerant when it comes to sending a cryptocurrency transaction. So we wanted to explore what happens if these messages, these delays, are withdrawn from different exponential distribution. It turns out it's actually a really hard problem to explore. And to explain why this is a hard problem, I would like to take a step back and explain what happens actually, how do we evaluate the anonymity when we have one type of traffic. So I'm going to take a very simple example. Let's say we have one mix and all the users, we have two here, or the senders, are using the same exponential distribution for these delays. So let's say Alice wants to send a message to Bob, and she creates her message, and then she withdraws the delay from an exponential distribution with the parameter lambda, and then sends a message to the mix, and this message will spend this delay inside of this mix. And then a few seconds later, a few minutes later, Marie wants to send a message to Charlie, and then creates her message, then withdraw delay from the same exponential distribution as Alice, and sends a message to this mix. After these two messages will be staying in this mix for a certain amount of time t, and then whenever the delay of each of these messages will be exhausted, then the first message will leave to the corresponding recipient, and then the second message will leave to Charlie. So here the adversary who is observing the input and the output of this mix does not know with certainty who is communicating with whom. However, can infer a probability by saying, well, there's two messages in, they're blended together, and then they will go to their corresponding recipient. So it's a half a probability for each of these messages, for example, to be from Alice's message. And this is achieved because there is a memoryless property of the exponential distribution. What the memoryless property says that these output messages are equally likely to be one of these output messages, regardless of the arrival of time. It's a nice property. This is why this type of mixing is being used, for example, in NIM. And it allows us to evaluate the anonymity of such system easily. But what happens when we have different traffic types? So let's say Alice, again, same scenario. Alice wants to send a message to Bob, and Mary wants to send a message to Charlie. However, right now they are using two different applications, and they have two different expectations when it comes to the delays. So Alice is sending actually an email, and she withdraws the delay for her email from an exponent distribution with a parameter lambda 1. Let's say it's the average delay is 1 minute. And then Mary wants to send an instant message using Telegram and withdraw the delay for her message to be spending inside of this mix from a different exponential distribution that has different average latency, and let's say for 5 seconds. And then the two messages leave to their corresponding. The adversary still does not know with certainty which message is going to whom, but the adversary here might actually have some guessing, because maybe the message that first earlier came from an instant message, because it actually we know that the average delay is smaller, right? So, and we cannot use, in order to evaluate the anonymity, we cannot use the memoryless property anymore, because blending these two traffic together actually disrupt this, and we do not know how to evaluate the anonymity. So with this work, basically, we're trying to explore all these different questions. Is actually blended traffic, is it useful in terms of anonymity, or do we actually harm the anonymity? And do other factors, such as the number of layers or the number of mixes per layer, do have an impact when it comes to anonymity? But most importantly, how do we even compute the probability? Meaning, how do we even evaluate the anonymity that is provided by the mixnet in such scenarios? So I'll just give like the intuition of how did we compute the probability. I will start with a very simple case. So we're going to have one mix, and we're going to have two types of traffic only, and we're going to assume the classic adversary in mixnet, which is a global adversary who's observing all the input and output. And in this first case, we're going to assume that the adversary actually knows the type of traffic of all the input messages. So what that means, when he's observing the network, he actually does know the number of messages from each traffic type that is being inside of the mix, right? Because he's a global adversary, knows the type of input, he sees them, so he can figure it out. So the probability of actually, let's say the adversary is focused on the Alice message, and the probability of an output message being this Alice message or being this target message, of course, will depend on the number of messages from each traffic type, which is given by K, the average latency of each traffic type, and the number of traffic type, which is given by this formula. It looks a bit difficult, but it's actually quite easy to understand. But what becomes really difficult is actually how do we compute the probability of the second messages, the second output messages, all the next messages that they are leaving. Why is that? Because right now, we don't have this K. We do not know, after that first message that left, the adversary does not know the number of messages from each traffic type inside of the mix. Why is that? Because the adversary does not know with certainty what was the traffic type of the first input message. The adversary simply does not know. So we need to rely on also in inferring the probability of all the possibilities of what could have been this first message. So the first message could have been the target message, Alice message. This is what the adversary is interested in. The first message could have been the same traffic type of Alice message, but it's just not the target message that the adversary is interested in. Or the first message could have been simply the other traffic type. And we need to compute all these probabilities in order to be able to compute the probability of all the next messages being the target message. And then we generalize our method for computing all the probability of the next messages and for when we have a big network, because the probability of these messages after these layers will also depend on the probability of being this target message in the previous layers. And we put all this math and this nice algorithm that I will not explain, but all the derivation and the algorithm are in the paper. So just like few results, so actually we do show that blending traffic actually is useful, if you trust me on this, and because I will not go into details. And then actually when we remember when we said the adversary does know the type of traffic of input messages, but even when the adversary knows the type of traffic of the output messages, we show that actually the anonymity level that we get is similar to as if we allocated to different mixnet to a different traffic type. So we don't lose anonymity when we are blending traffic. And then we also evaluated the anonymity. What if we have only one message from one traffic type and all the other messages are from the different traffic type? And in this case, we actually this one single message enjoy a lot of anonymity compared to like zero anonymity if we actually had simply two mixnet for different applications. And then, of course, the delay parameter of one traffic type will influence not only the anonymity for that traffic type, but also it will influence the anonymity that other messages from the other traffic type will have. So yeah, in this paper we have really great work, and we have very great math that is put in very great algorithm, and we also have empirical evaluation that shows different results and how these parameters interact with each other. And basically the gist of it, we show that blending different traffic types, whether it's 2 or 3, actually improves the anonymity that is provided by the mixnet in such scenario. And thank you for your attention.
All right, looks like we have a question up here already.
So thanks for your talking, it's very interesting. And now I have two questions. The first one is about the traffic pattern. Like the adversaries knows like where different type of traffic. And my question is like, if there is a malicious server, it knows where the traffic pattern of the incoming message, and then we see we have another malicious server that is the last layer of the mixed network. It also knows the traffic pattern of the message, and then it can just link those two messages based on the traffic pattern, and you see like you get a higher anonymity. And I'm thinking how you can get a higher anonymity in this scenario, because they can just link the message based on the traffic pattern. And for example, if we have 10% of message for one certain traffic pattern, and then we just decrease the anonymity set to 10% of the whole messages. And my second question is about like, so in this paper, we assume adversaries knows the delay of each traffic pattern. And my question is, if this kind of delay is unknown, so we just assume the clients add some random delay for each layer of mix, and what will be the result? What will be the anonymity? And can we use some proposed method in this paper to analyze this kind of unknown delay in each layer of mix?
So for this, for the second question, yeah, we do assume it's a public parameter. So I don't, and yeah, if you have like instant message that's being deployed, I mean that parameter, we don't know the delay itself because it's like a random. We're just going to have like an exponential distribution. The parameter lambda.
So you know the parameter lambda, right?
Yeah.
So like in my work, I just let the clients to use different lambda for each layer of mix. And then can we use your method to analyze this kind of scenario?
But why would you have different lambda for different layers?
I mean, also for higher anonymity, because if the adversaries don't know the distribution of the exponential distribution, and then it will be harder to link to message from the outgoing message and the incoming message. So that's my idea. So I'm thinking, can we use the proposed method in this paper to analyze this kind of scenario?
I mean, I'm a bit confused, but yeah, we can talk about it. But the lambda, the probability derivation will not be different if you just choose different lambda. Like it just you have in the paper you have this long math, and you can just plug any lambda you want. It doesn't depend on the specific lambda that you're doing, and then you can do empirical evaluation and see how that impacts the anonymity. Whether it's like the same.
But like the adversaries know the lambda, right?
Yeah, because it's public parameter. We're going to assume it's public parameter.
Yeah, but I mean, if we just let clients to choose some random lambda by themselves, and let mix know to sample the delay based on the chosen lambda, and yeah.
I have a question how this relates to the inter-arrival time of the traffic. For example, if you have one traffic class with a lambda larger than the average inter-arrival time and one traffic class with a smaller lambda, can you give some intuition about how that works?
Yeah, I mean, so as every academic say, it depends. But yeah, so actually we thought like, oh, the more, so eventually when one higher than the other, both anonymity will increase for both. Let's say we have two traffic types, one that has like very small, like 1 second, and the other one is 5 seconds, so it's close by, right? So eventually both of these traffic will increase. And then we have like different layers and then different levels of anonymity. Then we tried like 10 seconds, 15, but you reach a level where it's actually, this is the maximum they can benefit, and then the difference, the higher the difference gets, then like you kind of like diminish in return. And then it becomes like actually easier for the adversary to know that these messages are coming from different traffic distribution, and then you decrease the anonymity. You do not decrease it below what if you allow two different mixnet, but it just, there is an optimal level, and it depends on your parameter where you have to choose these parameters carefully. Does it answer your question? So if you have like a really high difference, let's say for one traffic type it's like 5 seconds and the other one is 1 hour, then eventually that's worse than if you have like 5 seconds to like, let's say, I don't know, depending.
Okay, I think perhaps it is best if this discussion is also continued offline in the interest of keeping our session on time. So let's thank Ines again.